All right, let's dive into a story that is just wild. It connects the deepest secrets of the cosmos with the phone you're probably holding in your hand. We're going to see how some of the most profound ideas in physics ended up solving one of AI's biggest, most expensive problems.
I mean, just think about that question for a second. It sounds completely absurd, doesn't it? Black holes and your phone. But believe it or not, this is the exact idea that unlocked a massive breakthrough. Stick with me and you'll see exactly how it all went down. So, before we can get to the genius solution, we really need to understand the problem. For a long time, the most powerful AI has been locked away in these massive data centers, really only accessible to a few tech giants with incredibly deep pockets. Let's dig into why. Okay, so at the very heart of how modern AI understands language is this idea of a semantic vector. Basically, the AI takes a sentence, or a paragraph, or whatever, and it translates the meaning of that text into a long list of numbers. This is how it can start comparing ideas using math. But here's the catch. That list of numbers is, well, it's huge. A really standard model, one you see all over the place, uses 768 different numbers just to represent the meaning of a single sentence. We call that a 768-dimensional vector. That is a ton of data for one little piece of text.
And this is where the scale just becomes absolutely staggering. Imagine you want your AI to search through 1 billion documents. Well, you need to store and process 1 billion of these gigantic vectors. You're talking about terabytes upon terabytes of data, and infrastructure costs that easily run into thousands or tens of thousands of dollars every single month. It's just been completely out of reach for almost everyone. For years, the industry's answer to this was just brute force. Bigger computers, more servers, more money. But this question changes everything. What if we've been trying to solve the problem with the wrong tools? What if we've been trying to solve it in the wrong kind of mathematical space? Now, this is where it starts to get really interesting. The problem isn't just about the size of the data, it's about its shape. Think about it like this. The standard approach has been like trying to pack a big, bushy Christmas tree into a regular old square box. It just doesn't fit right.
So, have a look here. On the left, that's how language and knowledge are actually structured. It's a hierarchy, right? It's a tree. You have animal at the top, and that branches out into dog, which then branches out into Labrador. But on the right, that's the digital space AI has been using. It's called Euclidean space. It's totally flat, like a grid. There's no natural tree shape built into it at all.
And that right there, that is the core of the problem. You are trying to jam something that grows exponentially, this tree of concepts, into a container that only grows linearly. So to make it all fit without all the concepts squishing on top of each other, you have to make the container ridiculously, absurdly huge. And that is why we ended up with 768 dimensions. So, okay, if a flat, square box is the wrong shape, what would the right shape even look like? What if you could find a mathematical space that was, naturally shaped like a tree to begin with? Well, it turns out that space actually exists. It's called hyperbolic space. It's this kind of mind-bending geometry that was discovered way back in the 19th century. And unlike the flat space we're used to, the amount of room in hyperbolic space grows exponentially as you move away from the center. It is the perfect, tailor-made container for language.
This is such a great way to picture it. Think of a circular map. In the middle, 1 centimeter might represent 1 kilometer. But as you get closer and closer to the edge of the circle, 1 centimeter might represent 100 kilometers, or 1,000. You're packing more and more space into each little bit. It means you have this infinite amount of room out at the edges to lay out all the very specific, detailed concepts, while the big, general ideas can hang out near the center. It's literally an infinite universe packed inside a finite circle.
Okay, so now we have the right shape. But how do we actually use it? And this is where the story takes a turn that is just so incredible, connecting this whole AI problem to Albert Einstein and his theory of general relativity. So before Einstein, we all thought of gravity the way Newton did, as this invisible force, like a rope pulling objects towards each other. But Einstein came along and completely reframed it. He said there is no force. What's actually happening is that a massive object, like the sun, literally bends and curves the fabric of space-time around it. And planets, they're just following the straightest possible path through that curved space. Gravity isn't a force, it's just a feature of geometry. And this is Einstein's whole profound insight boiled down to a single beautiful sentence. The stuff in the universe tells space what shape to be,
And in turn, the shape of space tells the stuff how to move. Now, look at this. Are you ready for the parallel? It's stunning. The breakthrough idea was, what if semantic similarity works the exact same way? The relationships between words, the semantics, tell this hyperbolic space how to curve. And that curved space, in turn, tells all the vectors where to place themselves. Finding how similar two ideas are isn't about brute force calculation. It's just about finding the shortest path in the right geometry. So, this is a beautiful, elegant theory. But here's the billion-dollar question. Does it actually work? What happens when you swap that giant, flat, expensive box for a small, perfectly curved one? Well, the results are nothing short of astounding. Okay, let's look at the hard data. On a standard quality test, the original, huge 768-dimensional model gets a score of 0.834. The new hyperbolic model, using only 32 dimensions, gets a score of 0.812. Look at those bars. The quality is almost identical. That is a 24 times compression. Just let that sink in for a second. We are representing the same incredibly complex web of human meaning using 24 times less digital space. It's like somebody created a zip file for artificial intelligence. And here's the most crucial part, the real kicker. What did we lose to get that amazing compression? Practically nothing. We've kept almost 98% of the original model's intelligence while using just 4% of the space. That is efficiency on a scale that nobody thought was possible. And this is what it means for the real world. A 95% reduction in cost. That system that cost you $4,000 a month to run, it's now $200. And it's not just cost. Searches run 25 times faster. A database of 1 billion documents goes from needing 3 terabytes of storage down to just 128 gigabytes. This isn't just a small improvement, it's a total game changer. This completely democratizes AI. It means a small startup can suddenly afford the same tech as a giant corporation. It means a farmer in a field with no internet can run a powerful AI on their phone to identify a crop pest. It means a small hospital can do advanced searches on its medical records locally, on its own servers, keeping that sensitive data completely private and secure. For years, those massive cloud bills were like paying rent to big tech to use their AI. With this, we're not renting anymore. We're buying the house. The landlord era of AI might just be ending. And this quote just captures the shift in thinking so perfectly. For years, the whole industry was just obsessed with making things bigger, more data, bigger models. But the real holy grail wasn't about more brute force. It was about elegance. It was about finding a smaller space with the perfect shape. And we'll end on this thought because it's just so profound. The idea that the same mathematical principles that govern the entire cosmos, things like curvature and geodesics, are the very same principles that unlock the deep structure of human language. It's incredible. It means geometry is no longer just a neat way to visualize intelligence. It is now a fundamental tool for engineering it. The next great leap in AI might not come from building a bigger computer, but from a deeper understanding of the very shape of meaning itself.